All right, so this week we're going to start out by looking at section 7.2. So it's the beginning of chapter 7 for us. We do not do section 7.1. And we're going to be looking at inverse trig functions. Okay, so we're going to get into a little bit more depth on what they look like when you graph them. So we might have done a little bit with inverse trig, at least how you do it on the calculator and the buttons to press. But we never really looked at a picture of them. Okay, so we're going to do a little bit of that today. So remember that in general, an inverse function is a mirror image of the original function. It's a mirror image over the line y equals x. All right, so let me graph an example that's a little more familiar, not a trig function. But let's graph square root function. What function is the inverse of a square root? I guess, yep.
Might be like y equals x squared.
Yeah, x squared. All right. Now we have to be careful because when you graph a square root, remember that only graphs the part of the root like that. That's a square root function. Now if we graph y equals x squared, that's a parabola. It has two sides to it. So the square root part doesn't. So what we want to do is graph a parabola, but we only want to graph the part that is greater than 0 in order to see the mirror image. So what I'll do is in parentheses, we've done this before when we did piecewise functions. I'm going to put a condition on when I want it to graph the parabola. Only for values that are greater than 0, because that's all I'm allowed to plug into the square root, values greater than 0. So I'm trying to compare the same thing. Okay. And I'll put in the line y equals x. And let's do zoom 6. So there's the square root. Ignore that part. There's the x squared. And there's the line y equals x. It might be better if let me zoom in on quadrant 1. So you can see it a little bit bigger. So the square root. There's x squared. And there is y equals x. So look at that. Can people tell that if you folded it right on that black line, the red graph and the blue graph would land on top of each other? Yeah, it's because they're inverse functions. And that's true for any inverse functions. They're always mirror images over that black line. So what we want to look at is an inverse trig function. Now, in order for a function to have an inverse, okay, it has to pass what's called the horizontal line test. Similar to the vertical line test, except the horizontal line test says to pass it, you need to have a graph. You can draw a horizontal line, and it only hits the graph one time. Okay, so look at the graph of square root. Okay, the one in blue. If I put a horizontal line, no matter where I put it, it never hits the graph in blue more than once. Does anybody disagree with that? No matter where you put it, I'm just looking at the blue one, it only hits it one time. Because it only hits it one time, it passes the horizontal line test, which means it has an inverse that would be a function. Okay. So now let's think about the graph of sine. What does sine look like? Graph it. Yeah.
It would look similar to like a sound wave that goes up.
Right, it's like a wave. Now, if you draw a horizontal line through that graph, will it hit it more than once? Yeah, so that's going to be a bit of a problem then. Right? It's not like the one that I just did before. Okay, so here's a picture of sine. If you put a horizontal line like that, it hits the graph more than once. That means sine fails the vertical line test. If it fails the vertical line test, then when you try to draw the inverse, it will not be a function. Right? And that's an issue. Okay? When we do inverse trig, we want it to be a function. If it's not a function, that means you get more than one answer. We can't have that. We have to be able to get single answers to these problems. So, does the entire graph of sine have an inverse? No. But does part of the graph have an inverse? Yes. All we have to do is position this so that we look at a section that passes the horizontal line test. And then we'll say that that section has an inverse. Not the whole thing, but just a part of it. Let's look at that section. Does that section that you can see inside that box pass the horizontal line test? What do you think, Raj?
Yeah.
How come?
Do you see the horizontal line test?
Yeah, does that pass the horizontal line test?
No.
No, how come?
It's the graph more than once.
It hits the graph more than once. So if you're trying to find a section of the graph that passes the horizontal line test, that's not it. So let's try sliding it a little more like that. How about now? Does it pass the horizontal line test? No. Still hits more than once. If we go too far this way, does that section pass? No. It hits more than once. So let's try something like, right about like that. Okay. Does that section pass the horizontal line test? Yeah. Okay. No matter where I put this line, I know it looks a little flat there, that's just because of the pixels. But no matter where I put this line, that particular section will pass the horizontal line test. That means that when you draw the inverse of that picture, the inverse will pass the vertical line test, and it will be a function. Yes? Yeah. So now, let's mark that and see if we can figure out where we are on the graph. Right about here, right about there. So let me move this off. Let's move this off. So we're basically at the minimum here and the maximum over here. So if we made a box, so now you can kind of see it in perspective with the whole function, we're looking at that section right there. What is this x value in radians? It's your first quarter point in the cycle. Yep.
Maybe pi over 2.
Yep, pi over 2. And what would be the left edge of this box? It's the low point in the previous cycle. Yep.
Negative pi over 2.
Exactly. So if we agree to limit the sine function to only look at the values between negative pi over 2 and positive pi over 2, then we can sketch an inverse. That will be a function. Okay. Is that the only section? No. We could have, if you put a box right here, that would have worked too. Right. Where I'm looking at that section, that's the most common section that they look at. Right. That's the way, when we do it on the calculator, that's how the calculator does it. That's how our book does it. Okay, so the solution to failing the horizontal line test, we're going to restrict the domain of sine to be from negative pi over 2 to pi over 2. What's negative pi over 2 degrees? Yep. Negative 90. And pi over 2? Yeah. Positive 90. Now, you might think if you limit the angle, or you limit how many degrees you can use, and that's what we're doing, that could cause a problem because we don't always work with angles that are between negative 90 and 90. There's lots of other angles. But think about a lot of what we do is working with what shape? In trig. Yep. Triangles. Okay. Specifically, we work a lot with right triangles. What kind of angle does that have to be right there? Oh, Nick?
It has to be less than 90.
Yeah, it has to be less than 90 because it's acute. All the angles in a right triangle have to add up to 180. And this is automatically going to be less than 90. So is this one. So is limiting our angles to only be between negative 90 and 90 a problem? No, not when we're dealing with right triangles. Right? This restriction is perfectly fine to do. So now, let's look at what the graph of inverse sine looks like. Remember, the notation for inverse sine is sine with a -1 that looks like an exponent. It's not an exponent. Or there is another way you can write inverse sine. Anybody remember the other way? Yeah? That's the reciprocal. That's cosecant. So that's a different function. What's the other way that you can write inverse sine if you don't want to use that symbol with the -1? Yep, that's.
Wasn't it like 1/sine?
No, that's what Vanessa said. Yeah. It's longer. It's 6 letters long. Begins with an A. Remembers that one? Arc sine. People remember that? Arc sine. So that's the other way you can write it. All right, so what was the equation that we said a graph and its inverse is reflected over? We said the graph and its inverse are mirror images over what line? Right? Right, y equals x. So think about what that means, y equals x. If you were using that in a problem where you did substitution, you would change y to x. Or you'd change x to y. Depends which way you're substituting. But the important thing to understand is y turns into x turns into y. That's what happens when you do an inverse. When we talk about domain, domain is what letter? Travis?
X.
X. And Greg, how about range? Is what? X or Y?
X.
So Travis said domain was X. Y. When you have the domain and range of the original function, how do you think that's going to compare to the domain and range in the inverse? What do you think is going to happen? They're very much related. What?
Could they be like maybe opposite or
No, they're not opposite reciprocals. But let's say you know the domain and the range of your original graph. How do you think you'd figure out the domain and range of your inverse? Ethan, what do you think?
Would you just like change the sign?
And what do you mean change this? Keep in mind this idea. This is a big part of it right here. That's very important. Well, let's go back and look at the graph that we just did. What's the domain of that graph in blue? About, anyways, what's the domain? No, the graph in blue. So this isn't, we're not doing trig anymore. So we're looking at that graph in blue. What is it? Well, it's a square root function, so remember, the domain might be more than what you can see. 0 to infinity, yeah. Okay, and if we look at the range, oh, that's also 0 to infinity. So that's actually going to be the same, so that's not a great example. But look at the range of the red graph. What do you notice about the range of the red graph? Yeah?
It's the same as the domain of the blue graph.
Yeah. Again, not the best example, but the domain of the blue graph is the same as the range of the red graph. Okay. So does that give anybody a hint at what happens with the domain and range? If you know them for the original, what do you think you do with them to figure them out for the inverse? Yeah? Yeah, you just switch them. Right? So if the domain becomes the range, and the range becomes the domain. All the x's and the y's switch places. So let's think about the graph we have right here. So just focus on that section in purple. What's the domain of that section in purple? Now we're back on the trig graph. Yeah.
Negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. That's the domain. And what's the range of that section in purple? Yeah.
Negative 1 to 1.
Negative 1 to 1. I know my box in red is a little bigger, but the purple section itself only goes up to 1 and down to negative 1. Okay. These two are going to switch. So now when we do inverse sine, okay, this is regular sine, inverse sine, the domain is going to be negative 1 to 1, and the range is going to be negative pi over 2 to pi over 2. So let's graph inverse sine. We'll set that window up, and that should show us a good picture. Let's clear everything here. Let's put in inverse sine. Okay, also I want to make sure that I am in radians. And I am in radians. So x, negative pi over 2. All right, that's negative 1.57. Just so I have a little bit extra space. Instead of going negative 1.57 to 1.57, I'm going to go negative 2 to 2. And, oh, wait a minute, that's the domain. Well, actually, I'm going to do the same thing for the domain. Instead of going from negative 1 to 1, I'm going to go a little bit more. So I'm going to do negative 2 to 2 on everything. I think that'll be pretty good. Gives me just a little bit extra, and that way it won't be on the edge of the screen in any direction. And that is the graph of inverse sine. Okay. So if we compare it to regular sine, notice that at the end of the function here, right at the edge of the box, the slope is starting to approach 0, starting to approach a horizontal. Same thing over here, starting to approach a horizontal. Look at it in the inverse. What's the slope starting to approach when you get to the very edge of the inverse? Yeah?
Undefined.
It's starting to approach undefined. It's starting to approach a vertical, right? Basically, everything about x and y switches places between the inverse and the original. Okay, and I know they look a little bit similar if you look quickly, but they're not the same. Right? They're definitely not the same. All right, any questions on that? So that's the domain and the range of the inverse sine function. We can modify that if we do transformations, but that is always going to be your starting point for inverse sine. Let's take a look at cosine. All right, so I'm going to put in regular cosine. I'm going to do zoom 7. And my first question, does this graph pass the horizontal line test? No. So that's a problem. Because if it doesn't pass the horizontal line test, then that means when you try to sketch the inverse, it would fail the vertical line test. And failing the vertical line test is bad. That means it's not a function. If it's not a function, that means you get an infinite amount of answers when you try to do the problem. At least with trig. We don't want to get an infinite amount of answers when we do inverse trig. We need one answer. So that means we need to find a section that passes the horizontal line test, and then our inverse will pass the vertical. Okay, let's try the same thing we did last time. Let's try negative pi over 2 to pi over 2. Negative pi over 2 would be right here. Positive pi over 2 would be right there. Does that section pass what's in between the red? The horizontal line test? No. So negative pi over 2 to pi over 2 doesn't work for cosine. Let's try that. Does the section in between the red lines pass the horizontal line test now? Yeah. So when we talk about inverse cosine, we're going to restrict it to just talking about this section. If we don't, we can't do the inverse. Are there other sections we could use? Yep, this one would work. But that's not a section that people normally use. Okay. That's what they use. Okay, so let's think of this as our box. That's all we're going to focus on. What's the left edge of that box at? Yep. 0. And how about the right edge? It's basically half a cycle of the cosine. Yep. Pi. Yep. So for the original, it's not the inverse, it's the original. The domain is now going to be restricted from 0 to pi. Yes, I know it really goes on forever in each direction, but we can't work with that. We've got to work with 0 to pi to make inverse happen. And what's the range of inverse cosine? Of cosine? Yep. -1 to 1. So now when we do the inverse, what's going to happen to my domain and range? Yep, they're going to swap. Okay? The domain will become the range, and the range will become the domain. Also, when we graph it, notice at the very end, it's starting to get horizontal, and it's starting to get horizontal. When I do the inverse, what do you think is going to happen at the very end? Yeah. It's going to approach undefined. It's going to approach something that's getting very steep instead of very flat. Okay. So let's write down the domain and range of inverse cosine. So -1 to 1 and 0 to pi. Okay, let's graph it. Oh, I need to clear that, sorry. Now, my X-min and X-max, oh, I changed everything, so let's fix it. If we do -2 to 2, that'll give us a little bit extra. And then on the range, I would go, let's go -1 to 4. This will just guarantee you're seeing more than you need to on every side, so you'll know it doesn't go off the screen. And that is your inverse cosine. Now, if I asked you to calculate this maximum point right here, the calculator wouldn't be able to do it, but you'd have to know what it is. What is the highest value that you hit? Yep. Pi, 3.14. Yep. And you hit that at an x value of -1. Right. Any questions on the restriction for inverse cosine? All right. Now let's look at tangent. Okay, we always start by looking at the regular function, then we do the inverse after. What's different about tangent when we graph that? Yep.
It's like less of a sound wave, more like hills or bumps.
Okay, can you give me, so yeah, I know kind of what you mean. Can anybody give me some more precise words to describe tangent? Yeah.
There are asymptotes.
There are asymptotes, absolutely. What kind?
Vertical.
Vertical. So when we graph the inverse, what do you think is going to happen?
That'll be horizontal.
It's going to be horizontal asymptotes, yep. Also, it still is a periodic function, meaning it repeats itself. And if we graph it, first question we ask is, does it pass the horizontal line test? No. So if you said you wanted to find a graph of inverse tangent, and you don't do any kind of restriction on the original, you can't do it. The inverse function would fail the vertical line test because that fails the horizontal. So let's find a section that we can look at. And this time I'm going to ask you. Anybody think that they see a section we could look at that would pass the horizontal line test? Yeah, Josh?
Like that middle section, -5/2.
Yes. We're going to look at this middle section right in here, from -π/2 to π/2. You can focus on any one of those sections, but that is the one that is commonly used. It's the one books use. Calculators do it the same way. All right, and you said that this left edge was what number? And the right edge? π/2. So -π/2 to π/2, is it going to be the same as that? What do you think? Is it the same the way we did it before? Just -π/2 to π/2 like that? Yeah? Right, you can't include them. You could include the -π/2 and π/2 when we did sine, because this is a connected graph. At the edge, that's not an asymptote. That was just our stopping point. But it does keep going. With tangent, that is an asymptote. Okay? So we're going to restrict the domain from -π/2 to π/2. And what about the range? What's the range of that section in the middle? Yeah.
-∞ to
-∞ to Okay. Same thing's going to happen when we do the inverse. Domain and range are going to switch, and the vertical asymptotes become horizontal. Okay, so this is for the original trig function. This is for the inverse. Okay, so let's graph it. So let's do inverse tangent. For our window, domain, well, you can pretty much do whatever you want because the domain, it's going to go left and right forever. But for the range, I would do -2 to 2. Okay, it just gives us a little bit extra so we can see it. And remember how the tangent curve looked before? It was mostly vertical. Now the tangent curve looks mostly horizontal. Okay, so that is the graph of inverse tangent. And if you want to see your asymptotes, you could put in negative pi over 2 and pi over 2. And there's your asymptotes. So that's the graph of inverse tangent. Any questions on that? So if you forget the domain and range of the inverse, I just try to remember the domain and range of the original, and then say, okay, switch up. That's the inverse. Because that is something we're going to have to remember. Okay. So what do we know about inverse trig functions? Okay? Like if I take the square root of 8 squared, what do I get? Yes, I'm getting 8 because I'm operating on a number and the operations I'm using are inverses. That's like adding 2 and subtracting 2. It's going to cancel out. So what would happen if I took the sine of the inverse sine of a number? What do you think would happen? Specifically to the sine and the inverse sine. Yep.
They would cancel each other
They
out.
would cancel each other out. Now, we just have to be a little bit careful because we impose certain restrictions. So yes, they will cancel each other out, but we have to make sure we're still respecting these restrictions that we put in place. Okay, so let's start with this one. Okay. There's 2 versions of every formula. One has the inverse on the outside, one has it on the inside. It's an order of operations thing. All right, so let's start with formula 1a. If you take the inverse sine of the sine of x, they will cancel each other out, and you'll get back what you originally typed in. Let's try something like the inverse sine of the sine of 0.25. So when I hit enter, what do you think I'll get? Yep, 0.25. And it worked fine. But if I do something like the inverse sine of the sine of, let's say, 2.6, didn't get back 2.6. And that's because the number that you put in here, inside, has to respect what you said right here. We have to be inside that box. So what was the highest and lowest x value we could pick and still stay inside that box for sine? Yep. That would be, that's the y value. Negative pi over 2, and then pi over 2. Yes. So in order to know when these formulas are going to work, look at the inside formula and ask yourself, what is the domain of the inside formula? That will tell you when the formula works. So if I did the inverse sine of the sine of 1.47, would I get back 1.47 when I hit enter? What do you think? Layla, what do you think?
What was the question?
Will we get back 1.47?
Yes.
Yeah, because 1.47 is less than or equal to pi over 2. Pi over 2 is, if you take 3.14 and divide it by 2, it's like 1.5 something. So that works. Now, let's look at the bottom one. Inverse sine. Based on the restriction we had up above and how I explained to find it, anybody think they can tell me when the sine and the inverse sine cancel out, when the inverse is on the inside? What would x have to be between?
-1.
-1 and 1. Yep. You have to look at the inside function and ask yourself, what is the domain of inverse sine? And if you can't remember it, like, well, I don't remember the domain of the inverse, okay, then think of the range of the original. It's the same thing, -1 to 1. All right, so a number that would work, sine of the inverse sine of 0.287. Gives me back exactly what I started with. Could somebody give me a number that does not work? Yeah. Yeah, 2.4. And the problem with this is you're not even going to get a different answer back than you started with. You're not even going to get an answer. Okay? It just gives you an error. And that's because when you look at inverse sine, we are completely off the graph. And when you say 2.4, you're on an area that doesn't even exist. Versus when you did it with sine, and we put in a value bigger than pi over 2, we weren't in an area that didn't exist. We were over here. So it exists, but the problem is we always get an answer that's in this box. So we got a different answer back. So when the regular trig function is on the inside, you will always get an answer back. It will match what you started with if you obey that condition. When the inverse is on the inside, you will not even get an answer if you're not between what you're supposed to be. All right, so let's try the formulas for cosine. Okay, so 2a has the inverse on the outside. What do you think the condition is to get back what you started with in formula 2a? The original value has to be between
0 and pi.
0 and pi. So is this a problem when we do right triangle trig, that sometimes you get the answer back, and then if you don't have the right condition, you don't? Nope. Because when we do right triangles, all our angles are between 0 and 90. This is the formula that you use a lot when you're dealing with right triangles, and this one. You end up having to take the inverse trig function, and it ends up on the outside. You're never going to deal with an angle in a right triangle that's smaller than 0 or bigger than 90. So this formula always works under the conditions that a right triangle restricts you to. Now, when we deal with non-right triangles, this idea would be a problem, because you could have an angle like 120 degrees. This doesn't work when you get that big. So we'll talk about something different when we get to that. How about formula 2b? Under what conditions would that formula work? Yep. Right. Think of the domain of the inside function. It's -1 to 1. And this is also the one that if you go off -1 to 1, you're in an area where graph doesn't even exist. So you will not get an answer. And formula 3a and 3b. Under what conditions do you think the top formula would work?
Between, but not including -pi over 2 and pi over 2.
Yes. So notice there is a little bit of a difference how I wrote the restriction. I didn't put the equal to under the less than signs. Where in sine, I did. All right, and how about formula 3b? What do you think the restriction is on that one? Yeah, effectively, there is no restriction. It's true all of the time. You could plug in any number you want in that bottom formula, and it would always work, because that's the only inverse trig function that goes left and right forever. You cannot end up on a space that's not on the graph, because the graph goes on forever. All right, any questions on those 6 formulas? And again, the versions that are the A versions, 1A, 2A, 3A, that's what you end up doing when you do right triangle trig. You end up taking the inverse trig function of both sides. The bottom one, we don't use that version as much when we do right triangle trig, actually, if at all. But we do use these other formulas for things you'll see later on. Okay, so transformations. Guess how they work? Exactly the same as every transformation we've done all year. Okay. So I'm not going to write it all down in detail. We've done it quite a bit. A is your horizontal shift. B is your horizontal stretch. C is your vertical stretch. D is your vertical shift. Is there any questions about whether it shifts up, down, left, right, stretches, compresses, or reflects? You should be able to look back in your notes several times and see that. And it's exactly the same for inverse cosine and inverse tangent. All right, so when we do a transformation, how do we figure out the new domain and range? Okay, it's not going to stay the same. If you shift it up, that's going to change the range. If you shift left or right, that changes the domain. All right, so how do we find the new domain? Well, there's a couple ways you can do it. First thing you have to know is what letters for the transformations, the A, B, C, and D, which 2 letters would affect domain? Josh? A and B, yes. Because that's the horizontal shifting and stretching. C and D affect the range. So what we're going to do when we're focusing on the domain, we're going to start with this. You're going to take what's in that blue box, and you're going to create a compound inequality. Just like these. These are all compound inequalities. You're going to put what's in that blue box in the middle. Okay, that's the argument. But when you have a compound inequality, you have a middle. You have an inequality sign, maybe you have something like that. But then you have a left and you have a right. Well, what's going to go on the left and the right? The original domain. So this is why you need to know the original domain. So you're going to put the argument in the middle, put the original domain on the left and on the right, and then you're going to solve for x. So just kind of an example. Let's say I asked you to find the domain of that. What's that 3 going to do to the domain? Yeah.
You're gonna have to divide by 3.
So it's going, can you describe it as a transformation?
It's gonna compress it.
Right, it's going to compress the domain. Think of the domain as it's symmetric over the y-axis. It's going to shrink in 3 times as much towards the y-axis. So when you set up your inequality, and I'm not going to do this whole thing out, I'm just kind of showing you how it works. You get your argument in the middle, and then your original domain on the left and on the right. What is the original domain of inverse sine? If you're not sure of the domain of the inverse, think of the range of the original. How high and low does the original sine go? Yep.
-1 to 1.
-1 to 1. Now, when you solve, you divide everything by 3, and your new domain is -1/3 to 1/3. That's how you do it. So it would compress the domain by a factor of 3. Okay, now, that's how you find the new domain. Well, the new range, very similar. We just have to take into account any stretching or shrinking first. That's C. And then any shifting up or down. That's D. So we're doing it in alphabetical order. So as an example, let's say you had sine of x plus 1 minus 3. Okay, just to use, I guess I can use the numbers that we should use. What's the original range of inverse sine? How high and low does inverse sine go? If you don't remember how high and low the inverse goes, think of how far left and right the domain of the original goes. Yep.
Negative pi over 2 to pi over 2.
Right. That's your original domain. This plus 1 is going to shift it 1 unit to the left. So that means all the x values should get smaller by 1. That's what happens when you take the original domain and you shift it 3 units. 1 unit to the left. How about this minus 3? Oh, wait a minute. Did I do? Oh, I did that wrong. I meant to do the minus 3. Sorry. Sorry, it's minus 3. I was going to ask, what does the plus 1 do to the range? I correctly said it shifts it 1 unit left. Oh, we're looking at the range right now. So what does the plus 1 have to do with the range? Yeah. Nothing, yeah. The plus 1 has nothing to do with the range. The only thing that's affecting the range here is shifting it down 3 units. Any question on that? Yeah.
Just for finding the new domain, do you use the original domain or do you use the inverse sine domain?
So when you're dealing with the inverse trig function, you want to use the inverse trig domain. Yeah. If you can't remember the inverse trig domain, then you could try to think of the range of the original because it's the same thing. Yeah. Okay. So new domain, put the argument in the middle, and put the original domain of the inverse trig function on the left and the right. Range, write down the original range, and then shift it however you need to or stretch it. In this case, that's the original range for inverse sine, and that's what you get when you shift it down 3. Numbers don't always come out very nice. All right. Let's try this one. Find the domain and range of inverse sine 2x. Let's see. Okay. So first of all, which one is going to be unaffected here? Yeah.
The range.
The range. There is no change to the range. What is the range of inverse sine? Yep.
Negative pi over 2, positive pi over 2.
Yep. Negative pi over 2. It's a positive pi over 2. You don't have to do that one first. I like to do the one that doesn't change. Okay. And my domain. Let's see. So we're going to start with the 2x in the middle. And can somebody else set up the rest of my inequality to find the domain? Yeah.
One is greater than or equal to 2x, which is greater than to -1.
Okay, can you give it to me with the -1 on the left side?
Oh, yeah. I think that's what should have.
So -1,
Negative 1 is greater than or equal to, or less than.
less than or equal to.
2x, which is less than or equal to.
Yeah. Okay. Now, when we solve that for x, can you give me my domain? I know that's an inequality, but can you give it to me in interval notation when you solve that for x?
Oh, that would be -1/2 the brackets. -1/2 to 1/2.
Yeah. When you divide everything by 2, that's what you get as an inequality, but most of the times they'll ask for it in an interval. Okay, so that compressed the domain by a factor of 2. Any question on domain and range there? Let's try this one. All right, what is not going to change this time? Range, so we just did it last time, -π/2 to positive π/2. And you might be able to figure out the domain. If you can't do it in your head, you could set up the inequality. But anyone think they can tell me the new domain of inverse sine? Yeah?
Would be -3 to 3.
-3 to 3, because the original domain is -1 to 1. This 1/3 stretches everything 3 times as much. So it's -3 to 3. Perfect. All right, let's try this one. What is unaffected this time? Yeah? The domain. Yeah, we're not doing anything horizontal. This is a shift up 2. So put your original domain. Original domain for inverse sine, -1 to 1. And what's the original range for inverse sine? Yep. -π/2 to π/2. And what are we doing to that? Moving it up 2 units. So if they don't want decimals, the only way to write the answer, I mean, you could find a common denominator, but that's fine like that. The range just shifted up 2. Question on that one? All right, let's try a different function. Let's do inverse cosine. All right, what is not changing in this one? Yep, Jeff.
Domain.
Yep, domain is staying the same. And can you tell me the domain for inverse cosine?
-1 to 1.
-1 to 1. Yep. Okay, range. What is the range of regular inverse cosine? No transformation. Just your starting range.
0 to pi.
0 to pi, and we're stretching it 5 times as much. So what would that range turn into if it stretches 5 times as much?
0 to 5 pi.
0 to 5 pi. And I think I had one more inverse tangent. Okay. Well, you don't even have to think about domain with inverse tangent. What is the domain all of the time? Every inverse tangent problem. Yep. Right. It always goes left and right forever. Doesn't matter how you stretch or compress or shift it. you can't change the domain of an inverse tangent. Range. What is the standard range for inverse tangent? Our starting point. Yep. Negative pi over 2 to pi over 2, including or not including? Not including. And we're going to stretch that 3 times as much. So it's going to be negative 3 pi over 2 to 3 pi over 2. Positive 3 pi over 2. Any questions on that? As far as the graphs of like inverse secant, inverse cosecant, and inverse cotangent, we're not going to get into those graphs. Okay, so this one says to identify the transformations that can be used to get that. And then it says find a complete graph. We'll see if we do that. Okay, first of all, how many transformations are there? How many? Yep, all 4. No reflections, but yeah, the four basic ones. All right. What's the first transformation that you always list? You don't have to give me like the number. I'm just wondering in general. You always tell me the
Horizontal shift.
horizontal shift. What is the horizontal shift here? Yep. I agree it is left, but not 8. Yep. It's left 2. Right? So this one's written in a little bit different format. You see this format on AP a little bit more, where they factor out the number in front of the x and put it on the outside of parentheses. Well, when you describe the transformations the way I've taught you, you would have to distribute that back out, at least to accurately see the left and right shift. I think everything else you can see fine without distributing it. But yeah, shift left 2. Okay. What would be the next transformation? Yep.
Horizontal stretch.
Yep, we're going to stretch by a factor of 4. So if they asked you, after you do the stretch, how much is it really shifting? It is 8 units. Okay? Because you're going to shift it left 2. So it's going to move 2 units left. But then you're going to quadruple that amount of shifting you just did. So yes, in the end, it will shift left 8 units. So that is another way to describe it. It's just not the way I've described how I taught you guys to do it. The way I taught you is we break down every transformation one at a time, okay? Instead of combining the stretch and the shift, right? Kind of idea. All right, what's the third thing that's going to happen? Yep.
Vertical stretch by a factor of 3.
Yep, vertical stretch by a factor of 8. Wait, by a factor of how much?
3.
Oh, 3. Did you say 3?
Yeah.
I don't know why I said 8. I like number 8. Vertical stretch by factor of 3. And the last transformation. Yep.
Shift down 5.
Shift down 5. Okay. So there's your 4 transformations. I'm not worried about graphing it. If we wanted to graph it, we would just have to figure out the domain and range to set our window. Okay, but finding the transformations, that was really the focus. All right. And the last thing, I think we've done this before, is using the calculator to evaluate inverse trig function. Can someone remind me, how do you get that symbol on the calculator? I know I've used it today, but I didn't really explain what I was doing. Yep. second, and then sine. Okay, so it gives you that as a decimal. Now, let's say that I wanted an exact answer. How could I use the calculator to help me get that exact? I mean, I know it's this, but how could I figure that out on the calculator? It's definitely a trick I showed you guys before. Yep, you do it in degrees first. If you're going to get a nice answer, it will come out nice in degrees. Well, so you get 30 degrees. And then convert that to radians by hand. Okay, the calculator will not be able to give you the pi over 6 because it doesn't know that 0.5235 is pi over 6. But you can figure it out. Now, this one is not one you could get an exact answer. I don't care if you do it in degrees or radians, you're never going to get a nice answer. So let's just write that it'll be approximately. 2 decimal places is usually a good rounding point. And I want you to think radians. Radians is kind of the default that we always use, unless the problem says degrees. Final answers should usually be in radians, and that's what you'll use in calc. Degrees is not used in calculus. So inverse sine, negative 0.7. Negative 0.78. Okay, and this one. What's going to happen when I do inverse sine of 1.2? Yep. Why? Pi over 2 is 1.57. So that is not greater than pi over 2, but you're thinking along the right lines. Yep.
Would someone just go beyond the graph?
Why? Where does the graph of sine, well, where does the graph of inverse sine end?
It goes from -1 to 1.
Goes from -1 to 1. This is outside the domain of inverse sine on space that doesn't even exist. So you can't go to 1.2. So when you try to do it, it's going to say domain error because you are beyond 1. Okay. So you just say no solution, undefined. Either answer is fine. All right, so that's 7.2 part 1. Okay, we could have gone faster through it, but I thought we went through it pretty good. So that is the homework for tonight on 394. We'll take a look at that first thing tomorrow, and then we will finish 7.2. And as far as right now, my plan is to be after school on Thursday. If you need to come see me or want to check in before the test.